This is the second video on electric fields. I recommend watching the first video first because parts of this won't make sense otherwise. So first of all, we want to look at the work done on a charge. If we take two parallel plates with one positively charged and one negatively charged, we will find that there is an electric field running between the two, with arrows showing the direction that a positive charge would be. Now, if we take our charge and we'll make it a positive charge, and we're going to move that a certain distance in this electric field. So we're going to move from there through to here. And we should really write the electric field strength as E written in there. It's a uniform electric field. We can tell by the even spacing of the lines as well. Now, the work that we're looking at, the work done on the charge, is same as any work, is force times by distance. So because it's a uniform electric field, there is a constant force that is being applied onto the positive charge by the field. So we would say that force due to the electric field is the electric field strength times by the size of the charge itself. And so if that charge was just sitting there, but we're applying this force in the opposite direction, just enough to overcome the field and move it a certain distance. And as I said, this equation here will apply. Work is force times distance. If we don't know what the force is, we can calculate it using the equation. Force is electric field strength times the size of the charge. Okay, so we can progress from this to find the work done per charge. So, oops, there we go. The work done per charge, we first need to substitute this into this. So we'll have work equals force times distance. Force is electric field strength times charge. So that's the force part times by distance. So the work is EQD. Now, it's really important at this point. Sometimes you'll see you'll have to calculate the energy transferred to that charge as it shifts in the field from one position to another. And sometimes you'll see it as E. And that's going to lead to a really unusual equation, E equals EQD. But this is where that little wiggly line underneath is important to take note of that. But anyway, the work done per charge, what we do for that is we divide the total amount of energy per charge. So we're going to do that to both sides of the equation. The right hand side just gives us more information. The left hand side is sort of our definition, and this work done per charge, or energy per charge, is what we call the voltage. Let's see, so if we're going to do a full equation, the Q's are going to cancel and we're going to be left with the voltage is equal to the electric field strength times by the distance. Okay, so voltage, if you like, can be defined as the the electric field strength times by the distance. But voltage is still, remember, defined as the energy per charge. And remember, work is in units of joules and charge is in units of coulombs. So that's joules per coulomb, which is what you might have heard that voltage is. Now the final little thing that we can do here, which is quite useful, is to look at a different form of this electric field strength, E. So remember that earlier on, electric field strength was defined as the force per coulomb, the newtons per coulomb, the force per charge. But we've got this other one arising from here. If we rearrange, we can get electric field strength is equal to the voltage divided by the distance, or the volts per meter. So we end up with two sets of units for electric field strength. We can have units of newtons per coulomb. We can also have units of volts per meter. Both are valid. However, the one on the right hand side, this one here, tends to be more practical because it's much easier to use a multimeter to measure the voltage and the ruler or a measuring device to measure the length. And whereas the force is very difficult to measure and the charge is very difficult to measure. So this one here tends to be much more practical to use. So don't be confused if you see the units different. Just remember they're both valid. Very often units are a abstract representation, and yeah, not to be, they inform you of a number of things, and there's a separate video talking about that.